Okay, I want to pull some of the things that we've gotten together and talk about how we use this eventually for an actual application here. And so I want to go back to how we find the electric field for a uniformly charged object. This time I'm going to have a uniformly charged plate. We're going to say it's positively charged like this. With a charge density, this would be on the surface because this is just a two-dimensional surface. So this would be a surface, a Q, this would be charge per area of the surface. And we're going to say this is a really big plate, really an infinite plate. Okay, it's not really infinite. There are no such things, but a very big plate. The idea here is that a piece of metal that's like the size of the house to a very small bug would look essentially like an infinite plate. So if you're close enough to it, it looks like an infinitely big plate, especially if you're like proton sized. So this is a very large plate with a charge per area given by this. And we want to, the first job is to find the electric field, say at some point marked with an X above the plate. So some distance above the plate. Okay, I'm not going to actually be that far away because I don't want to draw something that's that far away, but that's the idea. So we're going to say we want to find something at some distance away from the plate. Let's say it's actually a little closer like that. So we want to be able to use Gauss's law if possible. So as a reminder, Gauss's law is this integral of E dot dA on a Gaussian surface. Now our rules for the Gaussian surface is it needs to copy the symmetry that we have here, and it needs to include the point that we're interested in on the surface. So this is the point we're interested in the surface. So I'm going to make sort of a square plate like this, go down, and it's going to hit the surface, and there it is on the surface. Ooh. Like that. Okay. And we're going to let it just go ahead and extend below as well. Okay. I'd like it to be symmetric, but I want you to be able to see it. So there. So it's extending below the surface as well. Okay, so this is some distance, let's call it x above the surface, or y, I suppose. We'll call it a distance y above the surface that we're interested in. And so we need to know E dot dA on the surface, and so there are 6 surfaces because there's the top and the bottom and all the sides. And then we have to say is equal to how much charge is enclosed by our box over this epsilon, this constant that we keep throwing around. So on our Gaussian surface, the first thing we need to ask is what is the direction of the electric field? And if this is a really big plate, we can do the same sort of thing we did with a really long wire. That is, if I look at a charge over here and I compare it to a charge that's balanced over here, that both of these, the electric field due to both of these, kind of like this, the side parts are going to cancel out, and all I'm going to have left is an electric field that's up. And you can pair off any pair of points like that so the electric field is always up on the top. So on the top of this, I would have the electric field points like this, it points like this. We get rid of these sort of side pointing arrows here. And then underneath, we have the same sort of thing going. The electric field just points down. So what that says for our Gauss's law is that immediately this dot product on the sides, we've got E dot dA. Well, on the sides, notice our dA points off to the sides, right? Points left and right and forwards and back, which is 90 degrees. So that is E times dA times the cosine of 90 degrees, which is 0. So E dot dA is equal to 0 on the sides. So we just have the top and the bottom to worry about. So on the top, we have E times dA. dA points up, E points up, so we got cosine of 0, which is 1 at the top. And then plus at the bottom, notice in this case, E is pointing down. dA, there's our area from the top, from the bottom of the box, that's dA. Those both point down. So we also have the same thing on the bottom, E dA. And E, because every point of this is the same distance from the surface, that's a constant. It can come out of the integral. And then we just have the integral of dA. So that would be E times whatever the area of this box is. I'm just going to label it as A, and I'm going to say that's 2 of them. Okay? So this is a box. This box top has an area of A for right now. We'll just say that. And so this is the left-hand side of Gauss's law, the green side of Gauss's law, and that's got to be equal to however much charge is enclosed. Okay, so this must be equal to the Q enclosed by our box over epsilon naught. Well, the charge that's enclosed by our box is the part that's right down here, right? So the charge enclosed, if we use our density, which is this, charge per area, we can say our charge per area would be the Q enclosed over the area that's enclosed. Well, that area is the same as this area right here. And so Q enclosed is just sigma times this area, this charge per area times an area. So that is just equal to sigma A over epsilon naught. A's go away, and we get that the electric field is equal to, the magnitude of the electric field is equal to sigma over 2 epsilon, and it points up when you're above and down if you point below. It points away from the plates. Okay, so we've got a really big plate, and the electric field above the plate goes in this direction. It's E is sigma over 2 epsilon naught, and it points up. It's like this, sigma over 2 epsilon naught. And the thing to notice is that it is constant, and it doesn't matter how far away you get, because we assumed basically an infinite plate. So if it's an infinite plate, even as far away as you get, you sort of have a vision of an infinite plate. So you can start to see that when we get far away from a finite plate, this is not going to work anymore. But for a very big plate, this works reasonably well. So again, this is my electric field, electric field, all sigma over 2 epsilon naught. Okay, I'm going to add a second plate in, and I'm going to say it has the same charge, okay, the same amount of charge per area, another magical infinite plate, okay, but it's going to be negative charged. So this is also going to have sigma, the same sigma, but it's going to be negative. So what I want us to do is to look at the direction of the electric field. So the magnitude of the electric field is going to be the same, because we've got the same sigma of negative charges, same magnitude of it. So this, if we want to say, is equal to minus our pink sigma, if you like, but we're just going to say it has the same magnitude there. Okay. And we'll take care of the sign by doing the direction. So for this, notice that down here, the electric field is going to go this way. And so the electric field for the green plate is going to be up, and the electric field for the pink plate is going to be down, or the positive plate and the negative plate, and they're going to cancel each other out. So right down here, we're going to have that underneath this, we're going to have the electric field is equal to 0 underneath this plate. Above this green plate, we're going to have the electric field points this way. The electric field points, it's pointing towards, not away, sorry. above this plate, we're going to have the electric field still points towards the plate, so it's going to point down. So these are going to add together, but up here, again, this is going to point down, this is going to point down, and you can see that again, we're going to get above this plate, we're going to get an electric field that's equal to 0. And in the middle, right, in the middle here, these two are going to add together, and we're going to get, it's off screen, electric field is equal to 2 of these, or sigma over epsilon naught. So that's the situation. So this is one plate. This is 2 plates, one's positively charged and one's negatively charged. And this setup is called a parallel plate capacitor. Okay, so this is a parallel plate capacitor, where we start to characterize its capacity for holding charge. And the reason we talk about that is we think, oh, look at this pink plate. It's got all these positive charges. They don't want to be near each other, but they kind of like being near these negative charges. So this gives us a way actually to store charges. The charges actually sit on the inside, because these plates are not infinitely thin. They actually have a thickness. They're a conductor. And so these positive charges sit on the inside surface of the plate here, and the negatives sit on the inside surface there to build our parallel plate conductor. So the way we characterize them tends not to be in terms of the electric field, but in terms of the voltage. And when we looked at the voltage, when we have a constant, we're going to say just the absolute value of the voltage would just be E dot dr. When this electric field is constant, it's just E times the distance between these two. So if we call this distance D, then we have that the voltage difference between these two plates is just equal to our E, which is a constant, sigma over epsilon, times this distance between the plates. So if this is 12 volts, then that tells us how much charge we would have, right? Charge per area would tell us, if we know this is 12 volts and we knew what this distance was, that would tell us what our charge per area was, okay? And that gets us to our capacity. So capacity is something that is defined as, capacitance actually is what it's called. Capacitance is how much charge you can hold for a given amount of voltage. So the capacitance of something is equal to this C. I know we have C for charge, but this is C for capacitance, is Q divided by V. Okay, and so the units of capacitance are coulombs over volts, and that has a name of a farad, which we abbreviate with a capital F. So I want us to look at the capacitance of this parallel plate capacitor. How much charge can it hold at a given voltage? And it really shows up in this equation right here. So to look at the capacitance of this, we're going to use this equation right here and this equation right here. And so we're going to say the voltage, instead of the voltage difference, when I write voltage, it's really presumed that's the difference in voltage between here and here. Typically, if we have this one, say, at 0 volts and this one at 12 volts, then we would say 12 volts is our voltage difference here. So that's V is equal to, this sigma is our charge Q per area, right? And then there's a D over epsilon naught. And so I want to rewrite this so it's written as Q over V. So I'm going to divide through by V and throw everything else on the other side. So I will have area, the area of the plate, times epsilon naught over D is equal to Q over V. And that is equal to our capacitance, our capacity. Okay, so for a parallel plate capacitor, it's the area of this whole plate, which in your book you'll just see it as A, times whatever this constant is, this 8.85 times 10 to the minus 12, over the distance of the plate. And what this says is that if I hook up this to a 12-volt battery, so I have a 12-volt battery here, 12 volt, because I said it was 12 volts up here. Let's say that's the plus, this is the minus terminal, so the minus terminal goes here, and the plus terminal goes like that, and that's how it connects. Then that tells me how much charge I can hold how many charges are going to be on here if I've got 12 volts. If I double this and have 24 volts, then I'll double the amount of charge I can store. And so what happens is when you want to store some charge so it's available for later on, this isn't the most efficient way to do it, but it's sort of like a temporary battery. You charge it up. You could do it with a solar panel or something like that. You remove the cords, and then you've got something that's just sitting there, and it's got this charge on it, and it's ready for you to connect it up to a light bulb or your phone or whatever it is that you want to charge. So this tells you how much capacity you have. Well, it makes sense that if the area is bigger, you've got more room for these charges to hang out, these charges, these plus charges that don't like being near each other. That's sort of what limits things here, right? They just can't all sit on top of each other. So if the area gets bigger, it makes sense that you can hold more charges. Similarly, if you get closer together, this D gets smaller, right? So if something in the denominator gets smaller, this whole term gets bigger. That as this gets closer together, that you can hold more charge because these plus charges are less aware of their neighbors and more aware of the minus charge down here. Okay, that's sort of my description of what's going on. Okay, so you know, they don't really care about these things, but they're responding to the forces that they feel. And so you'll see that the equation for capacitance, for a parallel plate capacitor like this, you'll see that it's written as epsilon naught times the area divided by this D. So this capacitance just depends on the geometry. And so once you know the geometry of your plates, that can tell you how much charge you can store. And that's an important piece of information because this is still there and it's always there. Now, this does bleed off into the air because air has water, which are nice polar molecules. So this can discharge over time, but it is the case that capacitors can hold charge for a long time. So even when you have one that's not plugged into something, if it's just sitting on a shelf, say in a physics stock room, you can still get a shock from one of those. So very often when they're actually stored with a little wire that connects the plus and minus signs, so it will be safe.